Alright, now we're going to continue. Again, this is Dr. Mendenhall, Morehouse College, and we're continuing to go over some chemical equilibrium problems. But now we're going to continue with doing some more examples, and then we're going to probably finish out chemical equilibrium during this lecture section. So this should be on Wednesday, I think it's April the 3rd. And then after we finish this, we're going to move into acids and bases equilibrium. So again, you're advised to look at the Schoology feed for the notes that's posted there, as well as homework problems. So if we continue from segue into this next problem from the one that we actually did on Monday, what this problem does is we're looking at the same system, but something changes. The concentration amount changes here of what we actually had before. So when we read over this problem, I believe this should be example number 5. So it says, for the following reaction, where we have still our hydrogen gas reacting with oxygen gas, producing 2 moles of hydrogen iodide gas, we have initial concentrations. We have initial concentrations of H2, which is 0.00623 molar, I2, which is 0.00414 molar, and our hydrogen iodide, which is 0.0224 molar. And basically, we want to take this information again and solve the problem, but now the problem is asking us to calculate the concentration of each of these species, which is what this should say, concentration of all at equilibrium. Okay, so how will we go about proceeding with this? Again, we should have a strategy now in place about from what we've done before, and we can take that strategy and implement it now with these new steps, with the new given information. So from what we've known before is basically we write our givens. This is always our strategy in general chemistry with these particular problems. So we know we have given amounts of hydrogen iodide, and we have this, I believe this is supposed to be the final concentration of that, but let me, yes, this is saying our initial concentration of our hydrogen iodide is as stated here, so 0.000623, 0.00414, 0.0224, and this is all molar. And we did state before that from the previous problem the equilibrium constant should have been, what was it, 54.3. So given that we know all 3 of these, how can we actually proceed with solving this problem? So basically, according to what the word problem is saying in our context clues, is that we know all of our initial concentrations right now. So we would just simply write these in. Again, this is stating that all of this is molar concentration, so you don't have to write the units by the number of under the elements. So it's 0.00623, 0.00414, and 0.0224 here. Okay? Everybody should be straightforward. Initial concentrations for all of those are given to us. Now we need to go in and determine our change. So how will we proceed with determining the change for each one of these? Guess what? We've done this before. The same steps, the same process, the same strategy you had before with solving these, we're basically going to take the same thing and apply it here. The only thing that's changing with these ice charts, if you pay attention, is that your givens. What you may start off with, the givens you may start off with, that's what changes, and depending on what you know, what you're given, you have to basically tweak how you solve the problem. That's the simplistic way of determining this. Now, guess what? Guess how you get better at doing this? You have to continue to practice the problems. You can't just look at this once, look at this twice, and think you'll know how to do it. You have to be able to discern what you need to do with the given information, but it comes from practice, just like playing sports, just like conditioning, okay? Where you have to condition your brain so when it's time to take some type of assessment, some type of test, some type of standardized test, you've trained your brain enough to know when it's time to actually do the following steps needed. So, again, what did we learn from before? All we know is initial concentrations, and we have equilibrium constant that we know of, okay? Basically, that's it and that's all. That's all we know. We don't know anything that can help us calculate the equilibrium expression, so how will we figure out the change for this? This would, again, incorporate the negative x for the reactants, and the products would have what? 2x, because the 2 comes from the stoichiometric coefficient there. If a 2 is in front of here, this will be negative 2x. Okay? You'll do some problems with that a little later on to actually confirm the difference between these two. Now, from here on out, we implement algebra, we implement math. We have to start manipulating these mathematical operations, okay? So our equilibrium will be written as follows. So now for H2, again, we're coming down the column here. H2, we have 0.00623. This is what? Minus x. Then we have 0.00414. This is what? Minus x. Then we have 0.0224, and it's what? Plus 2x. I believe that should be plus. I don't think that's not. Yeah, plus 2x. Okay. Guess what? Now, what's our expression? The relationships that we actually know. Okay? So the relationships that we actually know of how we would write our equilibrium expression. I'll come over here just for the sake of board space. So we would write it as such. It's a little messy here. And we are simply going to plug our equilibrium line here into the equilibrium expression. So this is telling us we have the concentration of Hi squared over the concentration of hydrogen and iodide. Right? Now we simply plug in what we have here into this equation, and in doing that, we'll be able to solve the problem. Now, this is when those smart math people that we have in the class, this is where you can actually outshine. You can just go wild with this stuff, okay? Because this is one of those problems. Because we're going to have to roll back the pages here on how to solve this actual expression. All right? So with that being said, now we're going to go here, and we're going to plug in the information. I'm going to try and write it at the bottom of this just for the sake of board space before I move up. Now, if we write our expression here, KEQ, again, we want to solve for the x values. We already know the equilibrium expression, which is 54.3, but I'll wait to do that, okay? I'll wait to the end to do that. So we write 0.0224 plus 2x, that's going to be squared over 0.00623 minus x times 0.00414 minus x. Okay? That is what we need to solve for, okay? This is how we need to use this equation to solve for x. So all my math people, I pose the question to you. What would you do? What would you do? How would you go about proceeding to solve this particular problem here? Okay? Now, it's a lot going on. We don't just have multiplication things going on. We have some other things going on. So all the math people, let's figure out what we need to do. And all the engineers and everybody else. The doctor, medical students probably aren't too interested in this, but it's a good exercise to wake those brain cells back up. Okay? So, given this, we have 2x's here squared over this whole algebraic expression. What could we use to solve for this? That's the question. So I'll have you pause for that, and let's make sure this isn't going to mess up my focus, we now need to implement something that you probably have heard of at some point in time, hopefully, called the quadratic formula. Okay? Because it's not possible to solve this with the square, with this the shortcut of the square root bit, because of you have this plus here. So now, if we would go back, we can do this. Use quadratic formula. And somebody recalls of what this is. So this is our key here when it comes to these type of equations. Okay? So let's divert back to reminisce on what the quadratic formula is, and it should be negative x equals minus b plus or minus the square root of b squared minus 4ac, that should be right, over 2a. This is your quadratic formula. I'll write it again in a second just to make sure everyone can see it on the next board, okay? So now, let's proceed with writing this quadratic formula, and basically what we could do is let's carry out our multiplication steps first. So the first thing you want to do, and I'm not going to work through all the math, but I'll lead you in the right direction, okay? First, you want to carry out all the multiplication steps. That's what that essentially says, although it's hard to see, okay? And you can still see your quadratic formula sticking there. If we rearrange this, we can get 54.3. 54.3, where does that come from? That's your K value that was given to you, okay? That's where that comes from. Times 2.58 times 10 to the negative 5 minus 0.0104 x plus x squared equals 5.02 times 10 to the negative 4 plus 0.0896 x plus 4x squared. So that should be your numerator. This is what happens when that denominator comes back over. We did a FOIL method here. We did the FOIL method on our denominator, and that is how we actually went about solving this particular problem here. There we are. Alright, so again, multiply at the bottom. We did our FOIL method here. Then our top is essentially just multiplying all of those two squares out. You're foiling that all of this out as well. That's where the 4x comes from here. Now again, I'm not going to work through everything completely with the math. I'm going to give you some steps, but I'm not going to do all the intricate specific details. You can actually sit down and work through all those mathematical expressions and everything algebraically and carry out the multiplication. I'm going to just give you certain little hints along the way, okay? I'll be the stepping stool, if you will, all right? So now, once this camera continues to focus properly, we can go ahead and gather the like terms, okay? So now I'm going to pull all my like terms together. Again, if it looks like a math problem, we do what? We treat it like a math problem, right? So, let's rearrange this. So I'm going to say, collect similar terms or like terms. You've heard this before, I'm sure. So now we can rearrange some things to look at the following. 50.3 x squared minus 0.654x, okay, plus 8.98 times 10 to the negative 4 equals 0. Now, everyone, this looks like what? Quadratic formula. So, just for the people that are completely lost and maybe have never seen any algebra ever in their life before, I'll put the little variables over here, just like I do with templates, okay? So we got ax squared, bx, well, we can do it this way, bx plus c equals 0. That's what that's similar to if you've never seen it before, and that's supposed to be a blue marker. Now what we'll do is we will assign what our A's and what our B's will be. I kind of have them up under there, so you'll see A is 50.3 because it's the coefficients, just like with stoichiometry. A is 50.3, our coefficients, just like stoichiometry. B is 0.654, and C is 8.98 times 10 to the negative 4, okay? Now, we can now say if A is equal to that coefficient, B is equal to the following, and C and so forth, we can now go and plug it into our quadratic formula here, okay, up top. And when we do that, this is what we should get. We should come up with X is equal to 0.654 plus minus, which means you're going to have to do this more than once, negative 0.654 squared minus 4 times 50.3 times 8.98 times 10 to the negative 4. That should be all over this part at least. 2 times 50.3. Okay, so all I did here, what did I just do? All I did here was I just plugged in what I said A was, B was, and so on and so forth, and did the math according to the quadratic formula. So negative B is that, okay? Negative B comes into it, and keep in mind you have plus or minus, which tells us you're going to have what? 2 variables of X, okay? 2 answers for X, let's say it that way. 2 answers for X. So we have one X that should equal 0.0114 molar, and the other one is 0.00156 molar. Now, what you have to figure out is which X will actually work when you plug these 2 values back into your equation, your equilibrium equation. So what that means is that you have to try both of those out, but the one that really works is the smaller value here, and if you plug that one in, you will see why it does not work, because your values will come up to probably be a negative number, okay? So this is the correct answer, so now we simply plug it back into our so this would be the last step. So I'm going to just say step 3, because there's a lot of steps with this. We have H2 is equal to 0.00623 minus 0.00156, which gives us 0.00467 molar. This is again at equilibrium, okay, by 2, and we got HI. I'm not going to do all the math, I'll just give you the answers. 0.0258 molar, and HI is equal to 0.0255 molar. Okay, so these answers here are the final concentrations of your products and reactants at equilibrium, and you simply just get that by plugging it back into your equilibrium expression that we had above, the mathematical expression that we had above. Okay, so while you're finishing digesting that, what we also want to do is look at something else that happens when we talk about equilibrium. And we touched on one concept earlier when we were introduced, last class period, when we were introduced to shifting, of how the reaction could shift from left to right, or you may have more products produced or more reactants produced. So we briefly talked about what happens when you have a Q value that's less than K or greater than K or equal to K, how that can affect a reaction. But to be able to differentiate between the two, you have to actually know the initial concentrations to figure out the Q value. Okay, so that was what the reaction quotient brought to different to chemical equilibrium. Now let's look at something a little different. What actually happens when there may be an applied stress to our actual system? What could actually change with that? So that's what we're going to talk about next, and that concept is called Le Chatelier's principle. Now, keep in mind I'm not French, so it may be a little southern coming behind it, but just go with it, okay? So Le Chatelier's principle is basically helping us produce how equilibrium shifts when an external stress is applied to a system. Now, again, I strongly advise that you convert or reflect and use the lecture notes that I have already posted for you on chemical equilibrium, because some other ones on acid bases will be coming soon. Okay? So Le Chatelier's principle is essentially just that, and we can basically look at what happens when external stress is applied to a system. You can use Q to actually also help determine that. Now, how it basically works is, I'll give you a brief definition of it, and I think everyone probably has that top board. That bottom board here. I'll bring the top board back down. Got a little glitch here. Again, we want to look at basically an external stress. So what could happen is, say we have a chemical reaction occurring like we did when we talked about the ammonia, and say we add more nitrogen gas into the system. That would affect essentially what would happen to the equilibrium. That shifts things. That's what we're saying here. There's a shifting that occurs, okay? Now, let's define it a little bit more. Let's make sure I have a good focus here, and I don't think I do. I think I'm getting some glitches. All right. Le Chatelier's principles. Alright, and again, this is basically a general rule that basically allows us to predict the direction in which equilibrium may shift. Losing my markers. Predicts the direction in which equilibrium will shift depending on concentration, pressure, volume, or temperature. So these external parameters may have an effect on the system. That's what we're essentially saying here, what Le Chatelier's principle. Okay? So that's one general rule regarding this. Okay, but now we can also bring in a little caveat where we're talking about these four things which may provide some external stress. So that's what we mean by external stress. You have an increase in concentration, decrease in concentration, pressure, volume, or temperature. So I'll just reiterate that briefly. External. We're calling that stress just because it's an external parameter, not necessarily like a stress, but just some external alteration to the system, so we can just kind of refer to it as stress. So this is when we, again, bring in those four concepts: pressure, temperature, and volume. external stress is applied to a system at equilibrium, the system will offset itself. The system will basically offset itself or make accommodations for this adjustment. Will adjust itself to offset the stress. Let's say that. Okay? So that's essentially what we're talking about here, and we can do some examples. Basically, what the examples you'll work with are just basically letting you know that, say you may have more of something added to something else, and you predict what would happen, but we can also calculate a few things here. Alright, so let's do one quick example. Let's say we have at 350 degrees C, this system is at equilibrium. Say we can have N2O4 gas, 2NO2, and say we add more of our N2O4 is added. What happens is, as a result of that, as a result of adding more of our reactant, the system will offset and you will have a shift. The equilibrium will shift to the right. Okay? Now, you can also look at things where you may decrease a volume or increase temperature and things like that. And what I will do is I will put more examples to show you, to get clarification on Le Chatelier's principle on the slides that are posted up. Briefly, let me just do a quick temperature example. I think I have room over there, where we may have, for the example of temperature, we may have A plus B, where you have heat is going to be my delta here. This is going to indicate heat is coming in on my product side. This will result in a shifting to the left with the reactions, and we would have of the reactants, and we would have a smaller equilibrium here. Okay? And the opposite would happen if the heat was on this side. Okay, so heat is added to our product side here, causing a shift of equilibrium over there. You would get a smaller K. Alright. Keep in mind, you can still use the Q and K relationships to also help with this as well, especially when it comes to concentration. Alright, so that's another caveat I can actually put up here. Q, comparing Q to K also indicates equilibrium shifts. Alrighty. So again, I want you to look at your homework problems and also use those to go through with actually understanding what we've actually done here. So just to recap, what have we talked about thus far as chemical equilibrium? You've learned about chemical equilibrium. What it's saying is that there's not any change in forward or reverse reactions with the concentrations of our products or reactants. Okay? Another recap that we've talked about as far as chemical equilibrium is the fact that you have a homogeneous equilibrium and a heterogeneous equilibrium. You've also learned how to do what? You know how to write the chemical equilibrium expressions for homogeneous equilibrium and heterogeneous equilibriums, correct? Yes, that's correct. You also know how to do what? Calculate your equilibrium constants, which is the capital K. You also have learned how to what? Calculate your equilibrium concentrations, given that you know initial concentrations, and you don't know any equilibrium concentrations, or if you just know an equilibrium concentration constant value. Okay, so what am I saying to you? I'm saying that all those examples that I did in class, and especially on this video, those are your templates to help you figure out how to actually work these ice charts and go through these different processes. Your homework problems are set up to help you actually navigate through all of these things. These videos are also a resource to help you figure out how to go about doing these things as well. So you have to take advantage of all these things I've provided for you, and the fact that I've actually took the time to record these videos to help you understand what we're actually trying to do. Okay, so with that being said, now you again have to be able to figure out how all these different components come into play. K and Q, so you have equilibrium constant, you have reaction quotient. Now you can talk about how the system shifts according to Le Chatelier's principle, how it shifts to accommodate for this extra stress, and things like that. Okay, now we're also implementing more math, so where you have to do more algebra and you have to learn the quadratic formula all over again. Okay, so with that being said, we're going to switch gears and do talk about some acid and bases. Okay, so with acid-base equilibria, that means we're basically going to take information that we've learned from the actual chemical equilibrium systems, but we're going to apply it to acids and bases. Now, in the laboratory, in the teaching laboratory 112, we've actually started doing some things with acids, so this is appropriate for what we're actually moving into. So in the laboratories, you've been working with certain things such as hydrochloric acid and other things like that, which have been used to titrate, is the word that we're going to start to use, titrate with other things.